Now look at big data with Python, and let's see if we have it in 50 minutes or even shorter. And then Giant can start a little bit earlier. So it's 1 o'clock, so let's go here, second day, and we go to big data with Python. And I can also share the link in the chat like this. Okay. So what we will cover today is file format and also data types a little bit. I know that you have covered some of that in the Panda section. I know that it was mentioned at least. We will also talk about methods, how to work with if your data is big. It's about memory allocation, but also a method called chunking, where you basically can work with more data than is fitted inside in the memory. So a bit about file formats first. By now you know about bit and bytes. So I won't say so much about this. And numerical data, for instance, consists of 16 bits. 16 bits, if it's called short. It could also be single or double if we are talking about floating point. And you remember that, okay, so 32 bits that will cover 4 bytes in this case. So see, if we run with double, it will take twice as much memory. Text data, it could be, then it's only 1 byte. It's called character or char. And if you are more interested in some background, you have some details here. Yes, but in real scientific applications, data is complex and structured and usually contains both numerical and text data. So what we have here are some uh, uh, formats for data and storage. So we have tabular data, and that is basically tables. So you have rows and columns, and yeah, you see this, of course, in this pandas data frames, for instance. We could also have gridded data, which is quite common in modeling and environmental sciences. So it could be weather data or uh, yeah, like where we have parameters or variables described in different positions in the 3D world. So that's gridded data. It could be 3-dimensional or 2-dimensional. And yes, common data formats here, we will briefly mention this later on, is HA5 and NetCDF. There is also something called SAR, which is completely new for me. I will maybe learn something about this until next time. Then we have metadata, which is information about the data. And typically metadata is not very big size because it is only the description. But yes, for instance, in Earth and environmental science, yeah, we have practices. So for instance, we have netcdf files. Then the metadata is embedded directly into the data files. So that's quite nice. So yeah, for each, yeah, so it's structured in a way so that you can get information of a variable field. So what is it, and for which time is it valid, and such things. So we have the data about the data itself inside this structure. Then we have quite common comma separated values, CSV. So yes, it's basically matrices or tables. So it could be human readable as well. So it's often in text format. So it's easy to read. And here we have some, yeah, the packages needed, NumPy, Pandas, and some other things. And I see that it did not render correctly. So one can read about the space efficiency as well. This is rather bad, actually. But on the other hand, it's good for sharing. Yes. HDF5 is a high performance storage format for storing large amounts of data in multiple data sets. So it could be yeah, it could be weather data, for instance. So you can have a temperature and pressure and wind speeds and direction and everything packed into this data file. So yeah, you have this metadata also here. We have some best use cases and whether data sets is in array data format. So it could be gridded, but anyways, it could be array data format. What's new here is that this is in binary, so you can't read it directly, but it's more efficient in space, for instance. And here you can use pandas. Yes, and then we have netcdf also, which, as it says here, it's a data format that uses HDF5 as its file format. So, well, but it is a kind of HDF5 file, but the structure is standardized. So when you load this, you will know how the data is structured. So it's easy to get the data you want from this big database file or dataset file. And it also makes it possible to read from various different programs. So best use cases, working with data, big data sets in array data format. Yes, and good efficiency for space and good for sharing as well. And I don't think it's not included here, but SciPy usually uh, uh, can read netcdf. Yes. Then we have a package in Python called xarray that builds on NumPy but adds labels to multi-dimensional arrays. Yeah, so yeah, there are similarities with pandas, and it's particularly tailored to work with the netcdf files as well. So, for instance, these are some functions, how to read and also to write. And we will explore these in the exercise in the end of this session. So this was just a very brief overview of data files that could be interesting for you. If you want to dig deeper, there are some courses, Scientific Data and X-Array, these two courses. Yes, and we may have time after your exercises, and we can have a short, more deep discussion if you want to. Yes. So if we finish there and now continue with allocating RAM or memory. So in some cases, you will work with big data sets, and then you can actually allocate compute yeah, the compute cores or nodes to be able to load your data into the memory. So what you can do is to allocate many cores or a full node, and you do not have to explicitly run threads or other parallelisms to be able to do this. So it's quite common in bioinformatics where you have a huge genetic data, and then people can load a big node of maybe 512 gigabytes. They may run on one single thread, so it's no parallelisms, but they work with a lot of data. And then these cores can share the memory so that the memory can be filled up with the data that they are working on. Yeah, so the keyword here is shared memory, and that means that you can only work within one node. So you won't benefit by loading or allocating several nodes to get more RAM, because the memory for your program has to be within this node to be able to be seen by this program. Because as we saw in the last lesson, when you do MPI, message passing interface, you can use several nodes, but what happens then is that you will have one task per node. So you basically have a copy of your program, one copy on one node, for instance, and the other copy on the other node. And then they cannot share the memory. Yes. Okay, so how much memory do I get per core? Well, you divide the gigabytes of RAM of the booked node with the number of cores. So if you have a 128 gigabyte node with 20 cores, you will get about 6.4 gigabytes per core. It may be shown differently because this 128 gigabyte may be gigabyte maybe, and then things will be a little bit different. Or the opposite. So if I book 5 cores, then if we had this example with 6.4 gigabyte per core, you will get 32 gigabyte in total. So 5 times 6.4. So do you remember now how to allocate several cores? It's this long flag, -n, and then number of cores. And yeah, so if the common core memory, I mean node memory is 128, you may on your system find some nodes with more gigabytes. So you could of course also book these. But I will refer to the local HPC center's documentation in how to do so, because that may differ between. So if we just look at this table here, for instance, so we have the cores here per compute node, and at Kebnekaise we have both 28 and 72, or on some we have 128 cores or 256. Whereas at Rackham, it's more homogeneous. So it's always 20 here. On Snow, it's 16. And yeah, Cosmos is more 48. And memory can vary a lot. So on Rackham, we have between 128 and 1 terabyte. So we actually have a 4 gigabyte, a terabyte node, which could be a bit handy if you work with extremely large data sets, common in bioinformatics, for instance. Yes, so if you need more memory, you can either book more cores, or if the standard nodes are not enough, you can allocate those with more. So the standard ones will be the lower value here. So it's always 128, seems, but on Cosmos, it's always at least 256. On the other hand, if we divide 256 with 48, and in my head, it will be about 5 gigabyte. So on Rackham, it will be about, on Snowy, it will be about 8. So you will actually get more gigabyte per core on Snowy compared to Cosmos. So it's good to check this, how much you will get per core. Yes. But yes, we have a tool or a package called Dask, and that is how to use more resources than available, actually. And I copied this figure from Rebecca's Panda session. So you see here that we have this Dask here. So if you will need more than about 3 gigabyte in memory, you can go to this Dask. So, but this number can maybe be increased if we are thinking that each core actually have at least 5 gigabyte. So on our HPC system, I think we can increase this to 5. So as long as you are below 5, you may use pandas, I guess. Or do you have any comments on this, Rebecca, if you are here?
Yeah, you can. Yeah, 3 gigabytes is a very rough number. You can go up to like 5 or 6 gigabytes before you really start running into trouble.
Yeah.
And I mean, it also depends on your system. You might find that you can go all the way up to 10 or 12 gigabytes before you really run into problems.
Mm.
It also depends on the types of data that you're working with. Because 3 gigabytes in numerical data is not the same as three gigabytes in string data, because the string data can't necessarily be stored contiguously.
Yeah, okay. Mm.
So not all data are the same,
Yeah. So
even if
it's
they're the same even if they're
better
technically the
to.
same in memory. If they can't be stored contiguously,
Mm,
that can cause additional problem, slowdown.
yes. So uh, yes, so you should always allocate more memory than you think you need because it may require more than you thought. Okay. Now let's see. Do you think? Yeah, I think there was some rendering mistake here maybe. Okay, but at least Dask is very popular for data analysis and is used by a number of high-level Python libraries like DaskML. Will you say some words about this in the afternoon, Giant? I don't hear you. I don't think your voice is working. It worked too well before, but now it. Okay, yeah, we can leave it for now. But then Dask is composed of two parts. So we have, for instance, scheduling, and then we also have big data collections that we'll look at more below. Yes. Uh, so here we have some main level collections. We have, for instance, Dask array, which scales NumPy. We have data frame, which is related to pandas. And okay, this one is the same here. So it's not a collection in that sense. Then we have something called Dask bag, which you can read more about if you follow this link. What I think is the main thing that we can cover today in the limited time are these Dask arrays. So they looks and feels a lot like a NumPy array, but the Dask array uses the so-called lazy execution mode, which allows one to first build up a complex large calculation symbolically. So it plans, so to say, or so to speak, how to work with the data that you have or have created. And then it turns these calculations over to a scheduler for execution. So it consists of that it divides the array into small pieces or chunks, as small as necessary to fit into the memory. And then operations are delayed. That is laser computing. So we will have tasks that stands in a queue. And then no computation is performed until you actually ask values to be computed. For instance, print the mean value. Yeah, so data is loaded into memory and computation proceeds in a stream fashion, block by block. So instead of uh, running the whole matrix or what you have created at the same time and do the calculations, it's chunked up. So it is somehow, yeah, so it is defined chunk-wise. So uh, when the first chunk is created, it can be sent to the scheduler and you do calculations on it. When that is finished, the next chunk is created, and you can perform calculations on it. So it could look like this. So you import the array part from this DASK package. And in this case, it will create a matrix, random matrix with a size of 10,000 times 10,000. That will be 100 million cells. But you divide it into chunks which has a size of 1,000. So if you do the math here, you will see that this data matrix will consist of 100 chunks. Or in another way to speak, this matrix is divided into 100 different chunks. So it can run on multiple threads on your machine, or it will run on each thread at a time and perform the calculation here on each chunk at a time. It could also be distributed to several cores or maybe even nodes. It looks like here, but I haven't tried it yet. So and let's see, we can in a minute start, I think. Yes. I will give you now maybe 10 to 15 minutes to look at this. And you see here how to do. So I recommend you that you load where you are according to this. And I will actually say that you you should install these to your local if you don't already have it. And the reason for that is that when you do that, I would say that it becomes a part of the system for you. So when you load Python 3.11.5, for instance, you will also be able to use these. And the reason why you don't need a virtual environment is that now it will not crash together with the with the with the system module, because you so you expand basically the packages that is available. So you don't have any problems now with any version conflicts. Instead, you have a bigger environment. So I think this is a way to do as well, as far, when you are not working in specific project, basically. Yeah, and I think you can do this yourself, and then the exercises here can actually be done directly in the Python command line or in Jupyter if you decide to do that. So you don't have to actually book any course for this. I mean, an interactive session or so. So do it in the way that you are comfortable with. You may already have Jupyter on since the last session, then you can continue there. So please go through these. So it's first it's about X-ray, and I would like you to just explore a little bit and compare some things. And then we have the chunk size here, and then we have some questions here that could be by that. Yes, and then we reconvene in I think 15 minutes, and we can have a short wrap up. Okay,